There is a cold mark in the oldest light we can see. Not a planet, not a nebula, not a dark cloud blocking a telescope. It is a patch in the cosmic microwave background, the faint afterglow left over from the early universe. Scientists call it the cold spot. And after two space missions looked at it, the awkward part is this: it is still there. To understand why that matters, start with what the cosmic microwave background is. For the first few 100,000 years after the Big Bang, the universe was too hot and dense for light to travel freely. Space was filled with a glowing plasma of particles and radiation. Then, roughly 380,000 years after the beginning, the universe cooled enough for atoms to form. Light could finally move through space. That ancient light is still around us today. The universe has stretched it for billions of years, so it no longer appears as visible light. It arrives as microwaves, with an average temperature only about 2.7 degrees above absolute zero. But it is not perfectly smooth. Across the sky, the temperature changes by tiny amounts. Hotter regions and colder regions differ by fractions of a degree. Those tiny differences are not noise. They are the seeds of structure, the early fingerprints of the galaxies and clusters that would form later. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, to map those differences across the whole sky. WMAP gave cosmologists one of the cleanest baby pictures of the universe ever made. Most of what it found fit the standard model of cosmology extremely well. The universe looked almost exactly as the equations predicted. Almost. In WMAP's data, researchers noticed a large region that looked colder than expected. It was not just one cold pixel. It was a broad patch in the southern sky, often associated with the direction of the constellation Eridanus. Depending on how it is measured, the feature is described as roughly a 5-degree radius region and about 150 microkelvin colder than the surrounding pattern. That sounds tiny. A microkelvin is 1/1,000,000th of a degree. But on the CMB, tiny is the whole game. The entire map is built from tiny differences. So a cold patch that is unusually large, unusually shaped, and unusually deep gets attention. The first question was simple. Was it real? Maybe WMAP had a blind spot. Maybe foreground radiation from our galaxy had been cleaned incorrectly. Maybe it was an artifact of the method used to analyze the map. Then ESA's Planck spacecraft looked again with better instruments. Planck mapped the microwave sky with higher precision than WMAP. In 2013, ESA reported that the cold spot, along with another large-scale anomaly called hemispheric asymmetry, was still visible in the Planck data. That did not prove something exotic was happening, but it did make the simple, bad instrument explanation much harder. So what could cause it? The most grounded idea is a supervoid. A void is not empty space in the science fiction sense. It is a huge region of the universe with fewer galaxies than average. If CMB light travels through a very large, underdense region on its way to us, the expansion of the universe and the changing gravitational field can slightly affect the light's energy. That effect is known as the integrated Sachs-Wolf effect. In plain language, the light enters a cosmic valley, crosses it, and climbs back out. In a universe whose expansion is accelerating, the valley changes while the light is crossing. The light can lose a little energy, and the patch can look slightly colder. This is why the supervoid explanation became so tempting. If a giant underdense region sits between Earth and the cold spot, maybe the mystery is local. Not a scar from the birth of the universe, just a foreground structure altering the signal. But then came the problem. Surveys of galaxies in that direction did find evidence for underdense regions. The difficulty is size and strength. In 2017, a study in Monthly Notices of the Royal Astronomical Society argued that a supervoid could not explain the whole cold spot as a standard effect in the usual lambda CDM model of cosmology. That does not mean the void has nothing to do with it. It means the clean version of the explanation does not close the case. So the cold spot sits in an uncomfortable middle ground. It could be a rare statistical fluke. In a universe full of random temperature variations, some patch somewhere has to be the strangest one. Maybe this is that patch. It could be connected to foreground structure in a way we still do not model perfectly. Or, if you go further out, It could be a hint of stranger early universe physics. Some researchers have explored ideas like cosmic textures, or even collisions between bubble universes. Those ideas sound dramatic, but they are speculative. The cold spot is not evidence that a parallel universe has been discovered. The honest mystery is quieter and better. Our best map of the early universe is almost perfect, but in one place, it has a cold mark that survived a second look, resisted the simplest explanations, and still asks whether it is a fluke, a foreground effect, or a clue from the first moments of the cosmos. Follow the mind jolt for more.